So yeah, so Aditya already told you about eBPF, that it's a way to write programs and just like load them inside the kernel and run them at any hook or point where you attach them. So, but like from a compiler developer's point of view, a better way to like understand it, to be able to understand the verifier, is that eBPF is an abstract virtual machine, which is similar to the abstract virtual machine you have in C and C++. So the standard defines an abstract machine which hides over the details of actual machines which you program for. So there's some sort of undefined behavior, there's some sort of implementation defined behavior. But the problem with BPF is that all these programs run inside the kernel. So if people are being allowed to load them inside the kernel, you basically want to ensure that the kernel does not crash. It's not like kernel modules where you can just write random code and you can load them as root. So with eBPF, even if you are root, you cannot use BPF to like crash the kernel. So there is something between the actual running of your program and the loading of your program, which is called the BPF verifier, which we'll get to very soon, which actually does symbolic execution of your whole program, and it will ensure that all the invariants at runtime are enforced and your program will. So this also restricts how you do the BPF programming. But yeah, we'll go through a lot of examples and see what was possible and what is going to be possible. So just for the people who are new to this, there are different types of programs. So depending program runs, there are different kinds of restrictions and also different kinds of features you can use inside the program. So different kind of helpers, different kind of things you can do inside the program. So there is something called XDP, sorry, which is called the the full form is Express Data Path, which basically runs just after your driver DMAs the packet frame. So on the network card, you get the packet raw frame. The operating system DMAs it. Before it passes it to the kernel, you can execute a program to basically inspect the packet and do some kind of filtering on it, drop the packet or just pass it or redirect it to some other device. So this is actually mainly used inside big companies like Cloudflare and Meta, where Meta uses it for load balancing, quick load balancing without like entering the network stack. So just at the driver hook, and Cloudflare uses it for their DDoS mitigation stuff. So the verifier is actually the main core part of this whole BPF runtime, which ensures that all the safety properties, restrictions, and invariants are being held, and it is safe to execute this program inside the kernel, which actually reduces the effort you spend debugging your programs and writing stuff a lot. So yeah, so a lot of text, but we'll get to examples too. So, but the gist of the whole thing, the whole algorithm is that you have a set of instructions that you pass to the kernel. So you can write your programs in C, you can write your programs in Rust, you can write your programs in Go, Python, anything, and then the tool chain will compile it down to the BPF ISA. So it's similar to compiling it down to x86. So this BPF ISA, these BPF instructions are then passed as a program to the kernel, which will, the verification happens at the ISA level. So the verifier only sees assembly, but there are a lot of things like the type information that the BPF toolchain preserves, so that the verifier knows what is the type of the register and stuff like that. So for each instruction, it walks them one by one, and it basically simulates the actual instructions execution at runtime, and basically sees how you will affect the type of a register, the type of a stack slot, and stuff like that. So it models the whole heap, it models the whole stack, it models all the registers, and it will use all this information and statically analyze your program to ensure that everything is safe. And after like it is successfully verified, it jits your BPF ISA to actual machine instructions. So it goes from BPF ISA to x86 to ARM64, stuff like that. And then the page is marked executable, and then it is directly patched inside the kernel at runtime, so that you have native code execution. So there is literally zero overhead. It is simply just like you compile your program and run it inside the kernel. So yeah, and like if any of you have any questions, you can just stop me right in the middle and I'll answer you. Yeah. because that would be good. So we'll just go through an example. So this is a simple program where this is an XDP program. So the one I was talking about, where you have the context which contains the data pointer and the data end pointer. So data pointer points to the start of your packet and data end points right after the end of your packet. So comparing by incrementing data and like adding an offset and comparing it to data end, you can prove to the verifier, because these two values are unknown to it. So to statically verify that you do access within the packet bounds, it requires you to prove by using conditionals that you will be doing the access in the else branch inside that offset. So if we do data plus 8 is greater than data end, we know that the space between these two is less than 8 bytes. So our program is not useful if that is the case. So we just drop the packet. But usually, like when parse packets, the Ethernet header and the IP header is already there. So, and then it checks the type. So this is a simplified example. This is like not how you would do it, but to fit it on a slide. And then the type, the struct packet definition is here. So the type is of 8 bytes. So we already proved to the verifier that 8 bytes are okay to access. So it will allow us to do that. It will allow us to do the comparison. So this line is green. But as soon as we check for the port, which is beyond the 8 bytes, the verifier knows that statically it knows that the bounds of data are data plus 8, data plus 8. So it cannot allow you to access the port without proving that 4 more bytes are accessible between data and data end. So this program will be rejected. And then let's see another example. So this one is a tracing program. So tracing programs are like, so there is a kill system call inside Linux, so which takes a task pointer. So task struct is just the representation of a process, a task inside the kernel. So tracing programs can be attached before the function is called and after the function is called. So here we are like overriding the kill function inside the kernel. So we take the PID, we dereference. So you can dereference actual kernel pointers inside BPF, and we'll also see how that is made safe. And then you get the PID, you get the thread group ID, you get the name of the task in this buffer, so it knows that the buffer size is 32 because you pass the size off to the helper, which is BPF get task name. So it does not allow you to read beyond the 32 bytes. And this helper send signal sleepable allows you to basically send a signal to a task. So this is the kind of stuff you can do inside the kernel. And the first red line actually shows what is not possible. So you cannot basically typecast the task struct pointer to some other type and then dereference it. The verifier basically knows the actual type of the register one, that the first argument. So it will not allow you to dereference it as some other pointer type. So this is the kind of safety you get even at the bytecode level. You have type information preserved at the bytecode level, which the verifier uses to enforce the safety. And yeah, so now we get to some more complicated stuff that you can do at this point inside the BPF programs that you load.
Sorry to
Yeah,
interrupt. There's a question in the chat. Can I
yeah,
access PID of a process by a tracing program and pass it to XDP program using a map? Or is it
yes.
conceptually not possible since XPD rejects packets at NIC?
You can pass. So maps are a way to share data between programs. So you have a map, both programs are able to access it. So any data you store from one program can be read by the other program. So that is not a problem. I think what what the person was asking is that whether you can share the task pointer, right? Because PID is just an integer value. So if I understood it correctly, or maybe they can clarify in the chat.
Yeah, he says yes.
Yeah, so currently it's not possible, but like using something that there are patches that allow this stuff. So in the future you should be allowed to do that. So how that will happen is I'll just show the example here. So you will do something like this. You will take a reference to the task, and then you will. So this is the exact example you actually mentioned. So here we have a map. Suppose this map is accessible from a lot of other programs, right? So you can actually take a reference to the task. The verifier knows that you have incremented the ref count of the task struct. So if in this case, when you get a null pointer, you won't be allowed to call this BPF put task because there is no reference, right? It's just a null pointer. Of course, we can allow passing null and just doing nothing. It can be a no op like the free function in C, but right now we don't do that. And it also tracks, like it also does alias analysis. So suppose if I move this reference into another variable, and then I move the original reference out into a map, right? You move the ownership from your program, that the reference you took, inside the map. So you have passed the reference inside the map, and now your program does not hold it anymore. So even if you try to access that same structure using some other copy of that register which held the value, the verifier will know that it's a use after free. So this dereference, after moving it into a hash map, the reference will actually fail the load. So hash map's definition is just U64 and the value is task struct pointer. And yeah, so this can be your XGP program too. So you can move this value out of the hash map. So this is also similar to taking a reference, and then you can do anything with it, and you then have to release it because you moved the ownership from the map out into your program, right? So there is a concept of single ownership. Either a program has the ownership or a map has the ownership, and BPF like knows how to release a task struct because it can verify it at for your bytecode as well. So it will know if it finds a live value in the map. It will also know when it frees the map that it can drop the reference to the task. So this is another example where the verifier forces that the precise release of all resources and memory. So this will only pass when we do this, because before we exit the program, we have to account for the resource that we have moved outside of the map. So this is another example which, and like this is a bit of a contrived example. So there is a concept of a work queue inside the kernel. So it is like a thread pool where you can submit jobs, you can submit callbacks, you can submit data, and they will be executed at some point of time asynchronously. So so this is something that is not merged yet, but it is in the works. So you have you allocate some work where the function is BPF print k, which is basically a print function, and the data that you pass it is the string hello world. So strings in BPF always have a static lifetime, right? It's similar to having static lifetime in Rust. It's similar to having like raw data in C++. It's like that. So the verifier knows that this comes from a map which is like bound to this program. So it will allow it to pass it to this BPF work alloc, even if it execute asynchronously. So it can reason about the lifetimes of the data that you pass to this function. So that is also tracked inside the verifier, and it allows you to do that. And when we allocate it, we set the function to BPF print k and the data to hello world. And right after we submit, the kernel now has ownership of the work item. Just after you submit, you don't know when the work will be executed. Maybe it will be executed immediately, or maybe it will be executed right after some time, like after some time. But we cannot reason about this statically. So basically, these functions, the work alloc function has acquire semantics. You acquire some resource, and the submit work function has release semantics. So you basically release the ownership of the resource, and at that point the verifier stops tracking it, and it basically poisons the the work struct pointer that you have in your program. So if you do try to dereference it, or if you try to free the work item, like suppose due to an error, so it will always give you an error. So the red lines won't work. And yeah, so this one is actually pretty interesting, and it actually enables a lot of very cool use cases. So usually inside the kernel, you have tasks arranged in a linked list. So you have task next, then you have another task. It's like a linked list. So, but the verifier cannot know, right, whether the linked list terminates or whether the linked list keeps on going. So in a lot of cases, it would be too cumbersome to try to teach the symbolic executor in the verifier that which part is safe and which part is not. It would be a lot of effort. You have to annotate the places inside the kernel. It's totally C, so you are limited in what kind of annotations you can do, and then you have to read these annotations and understand them inside the verifier. It's a lot of work. So what we did in the verifier is, like in the runtime, so suppose that you load a chain of pointers. At this point, the verifier knows that it is an invalid pointer. Like it can be valid or it can be invalid. So there's a dual state that is tracked inside the symbolic executor. So when we do task, when we dereference this object, task PID is equal to 1, it will allow that, but it will basically handle the exception in case it is invalid. So normally when you do an invalid access inside the kernel, you get a kernel panic, right? You do invalid access memory, the kernel will print the stack trace and just reboot. But in this case, BPF registers a callback inside the kernel. So the mechanism is like this. There is a, it causes a page fault inside the kernel, and then it knows the instruction pointer which caused the fault, and BPF knows that this came from a possibly valid or invalid register. So it will basically patch the destination register to 0. So this only works for loads. So, and it will continue the execution of the program. So if you load task PID, it will appear to be 0 in the invalid case. So invalid reads are still safe. You cannot actually, so you don't even get random data. You'll get either 0 or some valid value. So even if you follow invalid pointers inside the kernel, it will allow you to safely dereference them, and this actually reduces the job of the verifier a lot. So this is actually going back to a very important point where developing the BPF runtime and developing the BPF verifier inside the kernel gives us a lot of opportunities for these kinds of optimizations, where we can lower the burden of the verifier by actually offloading some of that cost to the runtime. And this actually is used a whole ton inside the tracing programs, because there we don't know what is safe and what is not. And yeah, this is actually a very interesting thing that I think compiler folks will love. So like thinking about this, you might wonder like a program has a lot of possible paths that you have to verify, right? So if you do an if else branch, then you fork the states of the program into two, where you have to verify the true case, the false case. So how does the BPF verifier like avoid state space explosion? So how does it like avoid spending too much time exploring the possibly similar paths? So there's a very well-known trick inside the compiler literature, inside the symbolic execution literature, which is called pruning or state space. Like you prune the state space search. So by doing state equivalence. So the idea is the same, but I'll also show an example where it will be helpful to understand how the safety is also maintained while still like minimizing the state space. So a very simple example is this. So we are not concerned with what instructions one. So this is a 6 instruction program with a branch. We are not concerned with what 1, 3, 4, 5 are, but this instruction 2 is a branch. So verifier sets up pruning points inside your program. So a pruning point is where it will do these state equivalent searches. So suppose if your program goes in a straight line, there is no state that is forked, right? You just keep simulating the execution in a straight line. But once you have a branch, you have to fork the state, explore two paths, and reach the same path at some point after your if branch, after your true branch, after your false branch, right? So if you execute this branch at instruction 2, you go to 4. Otherwise, you go to 3 and then you go to 4. So 3 is skipped if the comparison is true, if both registers Rx and Ry are equal. So the verifier will first walk the straight line path. It will first walk 1, 2, 3, 4, 5, 6, and it saves the state at the pruning point. So the pruning point is the branch target, where both of those forked paths will meet at instruction 4. So it saves the state there, and on the second time, it will only walk 1, 2, and 4, and then it will do a state equivalence. So it came from the true branch, it stored the state at instruction 4, and then now it will come from the false branch, exploring skipping instruction 3, and then it will do the state match whether these states are equal, and if they are equal, it will not explore 5 and 6 again. So this actually allows you to just prune the entire state that you have to search again and again inside the verifier. If it can determine equivalence of the states that it is exploring, it can completely stop exploring the rest of the program after that. So this is actually what allows the current BPF verifier to scale. So it can verify 1 million instructions in under a second, and it can also like simulate the execution of bounded loops, and it allows them to work inside the program. And it also saves a lot of memory because you don't have to keep all the paths, all the states of each path around when you are exploring them. So I'll also show an example where I'll show an example how this works. So this is very fundamental to how loops are supported inside the program. So to avoid like unrolling the whole loop, like if you have 100 instances, like 100 iterations of the loop, to avoid unrolling the whole thing, it uses state equivalence to minimize the search. So if the loop state is roughly equal, then it will stop it, not explore again and again, and just move past the for loop. Yeah, so I'll show an example where this pruning works pretty well, and it will also give us a feel of like how the verifier actually proves the safety while minimizing the state space search. Yeah, so this is a program. So is Godbolt visible to you guys? Can you see it?
Yes.
Okay. So suppose that you get a buffer. So verifier knows what the size of the buffer is, right? It statically knows. Let's suppose that it knows that. So you have your program which receives a memory buffer, and you basically want to pass each element of that buffer to a function inside a loop. So the first path in this program is you set your size to 8, and then based on a random return value, you change it to either 8 or either 16. So there are only two possibilities. You have either the size as 8 or the loop bounds will either be 8 or 16. So let's see how the verifier will verify this. So first it will see that you store 8 in this size variable. So we'll not talk in terms of registers because that gets too tricky. We'll just talk it in terms of C. And then it sees that you have a branch, and by default it skips past this stuff. So it depends. It can take any of them. It depends on which one it wants to explore first. And this is the target, right? So based on true and false, both of those paths will eventually reach this point. So either it will be skipping over size is equal to 16 assignment, or either it will do that in one of the explorations. So this was just to show that the target is same as what I was saying. So I'll just remove this. Yeah, so once you do the loop, it will see that as long as you are accessing the buffer, it is still inside. So this path with size to 8 will be verified for like the size is 8 and whether this is within the bounds of the buffer. So the verifier will verify that. Now let's explore what happens when you do the return here. When you do the return, it goes back to this branch because now it has to explore the other path, right? It explored the first part with size is equal to 8. That branch is safe, and it stored the state at this point, the target. So when we reach the target again from the else branch, we will do a state comparison. So now we do size is equal to 16. So for this particular case, how the verifier proves the safety is, in the previous case you had size is equal to 8. Now you have size is equal to 16. Whenever you have a size argument, or whenever you have a scalar value that is used as an index or is used as a size, the old value should be bigger than the current value. If then it would not be needed to explore this the remaining 11, 12, 13, 14 again, because if it is safe with 32, it will also be safe with 16, right? That makes sense, right? So but in this case we proved the previous state with size is equal to 8. So we cannot say that size is equal to 16 is also going to be safe for this particular case. So then the verifier starts walking these instructions again, and if the size, suppose the buffer size is 12, then it will fail your program in this other exploration path. But if I make this 32, then the verifier knows that it already verified it with 32, so 16 is also going to be safe. So it will just skip exploring the rest of the program. So it uses so this might be familiar to people who work on compilers. It uses something called numerical abstract domain to track the ranges. So it can represent a range of values. So it can represent a variable offset. So the offset can be 0 to 4, something like that, and then it can ensure that one range is within the another range. So this inside the verifier, this is called tri-state numbers, but the better term for this is like abstract numerical domains. So yeah, so this was like a small intro to how the verifier does things, and now I'll also show a lot of other stuff that we are working on. So I'll share some other slides. So these are not my slides, these are someone else's, but the work is mine. So yeah, I'll share it. One second. Yeah. So right now we so is this visible? Yes, this one should be.
Oh yes, it is.
Okay. So this is similar to the program we discussed right now, right? It's like taking data, and then it is like taking the size of. The size of is known as a constant, so nh of is just a constant, and then the verifier sees that you can access the network header because you store the pointer eth as data, and then you verify that the size is within the bounds. You do the dereference, you access the data, the protocol, then you check whether it is IP or IPv6, and then you process the packet. So this is how things were done in the old style BPF C. Like we are moving towards a new way to write programs in BPF land. So this is from Catran, which is like the load balancer that Meta uses. And these are some of the new things that have been added over the years, which has greatly simplified and allowed new kinds of use cases to emerge. So whenever you access a structure, so you saw that programs can be. So whenever you do that, instead of the actual offset that you access, the field offset, the LLVM backend for BPF actually records the field name, the actual field that is being accessed, and it emits relocations which can be resolved by the kernel or by the tooling libbpf, the libbpf tooling which loads the program. So it actually allows you to relocate the field access, because what happens is inside the kernel sometimes some member variables are not available because of some config option. So to reduce the structure size, some elements are only compiled in ifdef config foo. So some of those members will only be compiled in when you have a specific config option set. So in that case, your program will break, right? Because you compiled it on your machine using offset 8, and now because of the config option, it moved up because those members before it are no longer there. So it moves to offset 0. Now your program will fail because offset 8 is not len or packet type, because you are accessing that. So instead of that, to work around that, to help with that, the LLVM backend instead like emits relocations. So they are similar to relocations like in normal C, but that allows you to basically fix up the offset when you are loading it on the system, on the machine. So before that, the access in is like symbolic, so it isn't resolved until the program is loaded onto the kernel. So this allows you to write portable BPF programs that can run on multiple machines, which are compiled running different kernel versions, even old kernels, new kernels, no problem. You can just run it, load it, and run it. And it also knows the type ID of each and every register, each and every stack slot at verification time. So all of this is, so BTF is like a compact type of dwarf. So it is like translated from dwarf, and then it is loaded inside the kernel. So each pointer's type ID, each struct's type ID. So there is always a type ID of each kind of struct, and the verifier uses this to track like what is the type and enforce like safe field access and stuff like that. And you like when you pass a certain pointer to a helper, it also performs the type check based on the helper's prototype. And then there's also this support where you can basically have kernel config options inside your program. So you can basically so they are resolved to a constant during verification. So if you do if config foo is enabled, then you can do some stuff in your program. And then so this is also in line with writing a portable program. So you can basically conditionalize your program based on a config option. And the best thing is that when that config option is disabled, the verifier knows that this is a constant, right? So it basically prunes, it basically removes that branch which was assuming it to be true if it is false. So then you don't even execute those instructions at runtime because the verifier knows that it is false. And this is something I already explained like before, but so this is the same thing where you access skb dev index. We don't know whether dev is true null or dev is valid pointer. So it basically hints to the exception handling code that this instruction may fault. So you have to basically patch it and let the program continue instead of crashing the kernel. So when you read 0, you know that this if index can never be 0. So when you read 0 from that field, you know that this was a exception that was handled from the kernels. This feature allows you to do is this is a type tag in annotate different parts of your C code. So you can annotate function parameters, you can annotate variables, you can annotate types, struct definitions with some attributes. So we'll see how we are using that to like extend the verification logic and make like even more things possible inside BPF. So in the kernel you have the per CPU tag where a certain pointer is a per CPU pointer. You have to like resolve it by adding the CPU offset to an actual per CPU pointer, the actual pointer value. So the verifier needs to know that this is not an actual pointer, right? It cannot allow you to access that invalid value as a pointer. It needs to know that this is per CPU, so you have to translate it first before being able to access it. Similar with user pointers, you have to like handle the page fault, possible page fault for user mode accesses when you are doing that. So all these hints are possible because of this feature which was added to the LLVM backend. So this can be like enabled in normal C as well, but for now LLVM only allows it for the BPF BPF frontend. So yeah, so this is something that I am working on. So I have to still like respin this patch. KPTR new is actually, so this actually takes, instead of the size like compared to the actual malloc in C, this actually takes the type of the structure that you want to allocate. The size is automatically determined from the type because the verifier knows it. So when you get the return pointer, it knows that the size of the return pointer will be 4 because there is only an integer inside. So this is a struct foo with the integer value. It also knows that it is a struct foo. So when you do BPF KPTR new, you pass the type ID and then it allocates and gives you the variable. And then you can do a map lookup, and you can also store these kinds of references. So this KPTR ref is basically a type tag which we talked about in the previous slide. So this actually allows the verifier to see that this pointer has ownership semantics. So you basically own the foo pointer inside your program, and now using this exchange, which is similar to std swap, or if you know Rust, then it is similar to like moving the std boxed pointer inside, like it gives you move semantics basically. So it moves from your program to the map. So you exchange the pointer that you hold into the map. So either the map holds the reference or you hold the reference. Both of them cannot hold it at the same time. So the verifier can reason about the ownership statically, instead like using these invariants that are enforced using these helpers. So this allows you to build your own objects inside BPF, and like it opens up a lot of use cases. And this is actually pretty something that this is also part of the previous set that I'm sending. So this allows you to basically prove statically whether the locking invariants for lists, arbitraries, and possibly even other more complicated cases are held at, you prove that statically. So suppose you have a global list and you have a log that protects it, and this contains is actually telling the verifier what kind of struct this will contain. So in the kernel we have these intrusive linked lists where the node resides inside the object itself, and then you do something like this BPF list add, where you pass the node and the head, so it links your structure directly into the head. So instead of like having it like C plus in C++ you have std list, which basically allocates the elements inside instead of like intrusively linking them. You can allocate the object separately and then link it inside your linked list. So the verifier knows that you have to hold this lock because this linked list can possibly be accessed from multiple CPUs, and similar for this RB root, which also has a contains macro to tell it which structure it links inside. And then the verifier will enforce that you cannot do this BPF list add BPF list add or BPF RB add without like holding this BPF spin lock. So you have to hold it, and then before exiting your program you have to do the unlock, because you cannot like lock and just exit your program, because that would lead to a deadlock when someone else tries to acquire the spin lock. So all of this is like never checked at runtime. All of this is enforced statically. And like this is also something that people are thinking about. So it's similar to exceptions inside C++. So this will actually be very familiar to compiler people. So what we want to do is, now that the verifier has knowledge about what function you must call to release a certain object, what locks you have to take, it also tracks the locks. So basically it knows everything about your program state, right? So if it can enforce that you have to release the lock or you have to release the object, it can also do that on its own, right? If you suppose if you do a panic inside your BPF program, or if an assertion fails, the verifier can generate an exception table and basically unwind your stack, release locks, call all the destructors, and basically poison your program when the assertion fails. So why this is being introduced is, it's not always possible for the verifier to infer the context, right? This CPU DOM ID map that it is accessing may be declared in the kernel without a bound. So you can declare external variables without an array bound. So to how do you infer that you can access it with less than max CPUs within those bounds? So assertion is a way to basically tell the verifier that this condition will always be true, and then there is a runtime check, and then if in the else branch the verifier inserts a panic. So if your program violates the assertion, then your program will be poisoned and it won't be running again. But if it does not, then you basically make the job of the verifier easier in some very complicated cases, and then you can you can actually do whatever you want after that, like in those with those invariants set. So, and the good thing about this is, even if that is a runtime check, mostly that branch will be untaken. So the CPU can basically speculate past that pretty easily, because in its branch prediction table, it will always see that this at this instruction pointer, this branch is always untaken. So there is literally no cost except in the slow path, which will almost never be hit, which should not be hit when your program is correct. So yeah, so the main premise here is that everything should be safe. So we like in the BPF land, our goal is like more ambitious than Rust. Like we do so Rust will allow you to leak memory. Rust will allow you to do borrow checks at runtime. So it is a hard problem, but at least for now, at least for these limited cases, we are able to provide like precise tracking, precise static analysis of things. And one benefit that we have over other kinds of similar projects is that we are tightly integrated with the kernel. So we can like encode those invariants, those semantics inside the static analyzer, which is actually not a very good thing if you think about it. But if you are able to do that, then it like opens up a lot of use cases and makes your life a lot easier. So yeah, so the end goal of this whole exercise is like eventually the goal is to write actual kernel modules inside BPF. So we want to write portable, dynamically compilable kernel modules. Like most of them are developed out of tree, like which users load, to still be safe and as capable as actual kernel modules, which are basically loaded inside the kernel. So yeah, this is where things are moving in the future, and like there are a lot of cool things that are coming, like still in the works. Like you should be able to run BPF programs inside kernel threads, so you should be able to possibly implement something like memcached not very far in the future. That is like something we are discussing in the upstream mailing list. And like it would be pretty cool, like because you can directly take the request from the driver hook, so you can compose your memcached style application using multiple BPF programs. You have one request processing thing at the start of your network driver hook, which takes the raw frame, then it queues it inside a linked list using this stuff, this safe linked list API. So you can put stash the request for later processing by the BPF program running in a kernel thread, and then it can basically, so it's a queue, right? You basically queue it in the linked list, so you can push into the queue, then take the spin lock, pop out of the queue, and do the request processing. And then you can basically take that request and rewrite it in place. So there are no copies, right? You take it from the driver, rewrite it in place, and then you can send it out again. So it should be much faster than what we currently do in user space, all thanks to all of these primitives that we are able to use. So yeah, so the end goal is to program the kernel in BPF. So that is where things are heading into the future. Like that would be it for my presentation.
Awesome. Thanks for the presentation. I'm sure people would have questions. I had one question. In one of the slides, you were saying that when you move the variable to hash map,
Yeah.
the BPF verifier would know that the ownership has been transferred. But what
Yeah.
if I just do plain assignment? Like, is it possible or not at all?
If you do a plain assignment, it won't allow you to do a plain assignment. So it only allows that kptr exchange helper to actually move the ownership. So you cannot do a plain assignment to that field.
So I cannot do plain assignment to any global data structure. Is that the case?
No, you can do it, but when you are working with owned pointers like this, these kptrs are owned pointers. So in that case, when you are moving the ownership, you have to use an atomic exchange, because you have to move it atomically to the map which is accessible from all the CPUs, right? So it has to be atomic.
Okay.
Yeah.
Makes sense. There is one more question by Rahul. Could you explain BTF core in simple words to me? I do not have good intuitive understanding of it.
Yeah. So core is basically compile once, run everywhere. So BTF is actually, so you have debug information in your C++ programs or C programs, right? The GDB can show you the source code. GDB can know the types of the variables. So this is similar to that. In BTF, all the types that are used in your program are emitted to the BTF file, and then that BTF is loaded with your program inside the verifier. So you tell to the verifier that this is the type information for my program, and this is my program. So the instruction will actually tell it this, like it will emit that this is the ID of the struct that I'm working with. So the verifier can actually track everything and enforce. So if you are accessing the argument of a tracing program, which is a socket buffer, so you load the first, you use the first R1, the register 1. So it knows that this is the SK buff struct. So it will only allow you to access the fields within bounds, and even the field access has to be precise. So if you are loading the protocol field, which is a U16, you cannot do a partial load of that. You have to do a complete U16, like 16-bit load of that. So the core, very simply, is that so this was BTF, and core very simply is that whenever you do these field accesses, instead of the actual offset, the LLVM backend, which can generate BTF as well, also generates symbolic access. So instead of like emitting R1 plus some offset, it emits R1 plus some offset, R1 plus 0, and in the relocation table, it will like add an entry for that instruction that this is a relocatable instruction. So you have to relocate it to the protocol field of the skbuff.
Nice.
So yeah. So
Penil again wants to know. Sorry, someone was speaking. I don't know who was speaking. If you can, if you want to speak, just go ahead. No. Okay, that's okay. So another question from Penil is some pointers to start contributing to BPF and maybe convert full time.
yeah, so the way I started was, so I actually began working on it, like on the verifier stuff, like last August. So I guess I've been doing it for a year now, more than a year, a little more than a year. So how I started was, you have to pick a problem, right? You have to start from somewhere. So that is the most, like the hardest part. So you pick something that is unimplemented, something that is something that people, so the first thing would be to start reading stuff on the mailing list, see what people are talking about, see what is missing. So sometimes when people send patch sets, they'll write what are the future steps that can be done inside the cover letter. So that you have to be on the lookout for that stuff. So if that is something that you know about and you can implement it, you should actually take a stab. So people will actually welcome your patches even if it is wrong. So the first time I sent a lot of stuff, like I respun the same patch set 7 times because I was doing it wrong for 7 times. But still, like, people stick with you, and like they want new people to come in and they want people to contribute. So finding your niche, like something that you know a little bit about and you can build up upon it, and you see that people need it, is like actually the best way. It's a bit hard in the kernel because there's no roadmap or to-do list, so you have to like spend time and effort finding that on your own. But yeah, that would be if you want to go inside the kernel stuff, like user space is a lot easier. So libbpf, you can see there is a issue tracker on GitHub for libbpf where there are like fuzzing related crashes and stuff like that. So you can see, you can try fixing those to like get a feel of how the code works. But yes, like starting somewhere and getting your hands dirty would be the best way.
Nice. I have a question.
Yeah.
Can we run the BPF let's say I want to write a C program compiled to BPF in Clang, and then run the verifier just for my personal hacking account. Is it possible?
Right now, it's not possible to run it in user space. So you will have to load it inside the kernel, but it should be possible. Like there is nothing very specific, like except this exception handling stuff, which is like tied to the kernel. So if you ignore that part, it should be possible to run it in user space. So conceptually, there is nothing. So there is actually a verifier implementation which uses like SMT solvers, like it uses abstract interpretation. So there is something called Prevail. So I'll put the link in the chat.
That will be an interesting project, Fenil, if you are looking for it.
Yeah. So if you guys are interested, you can actually look at the paper. They actually have a paper describing their implementation, a very nice paper, and a lot of ideas from that paper have actually made their way into the Linux verifier. So there has been a lot of cross-pollination of ideas. Yeah. So this one can run in user space. This is actually what Windows for eBPF uses for their. So they run it in user space using as a trusted process. Because the main problem with running it in user space and then accepting the verified program is the trust between the user space and the kernel, right? Because it runs, so it basically the verifier has to be part of the trusted computing base somehow. So some concept of a trusted process if you want to run it eventually in the kernel, something like that. Yeah.
Okay. So the verifier, is it? So my question was like, I'm not looking for loading the program. I just want to run the verifier. Like, is it a correct verified program or not? Even if it is correct, then I'm not going to force kernel to take it without verification. It's just for testing purposes.
Right. So you basically want to reuse it as a static analyzer, basically.
Yeah.
Yeah, right now it's not possible. I mean, you can just try loading it. It will throw errors and stuff like that. But right now it's not possible to run it in user space. Yeah.
Okay.
And like just do the load and not JIT the program and stuff like that. That is also not possible right now.
Okay. Yeah, that'll be pretty interesting, I guess, especially for large scale development.
Yes, yes, people have actually been thinking about that, because eventually you want like language servers to provide hints while you are writing your BPF program. So
yeah.
it can do that, but if only if it is able to like do that kind of execution dynamically and without like loading the program, actual program inside the kernel.
Okay.
Yeah.
Nice. That's pretty interesting. Anyone has questions? No. That's okay. One thing I wanted to mention was like if you look at the application of BPF, there are several companies. Like for example, as Kartikeya mentioned, like Cloudflare, there is CrowdStrike. So during the COVID, if you see, like there has been a lot of issues with security, like online presence of people
Yes.
increased, and so has the hacking and everything around it. And so you can think of like next 5 years, security is like a very big opportunity for people like working on startups, etc. And BPF comes as like a lifesaver for enabling many of these technologies. And there has been already companies like CrowdStrike, Cloudflare, but new
Yeah.
things are coming up, and a lot of
Yeah,
things are being
there's also a startup like called Isovalent, which does like they have their own network like bypass network data path based on BPF, which is called Cilium. So
yeah.
that is pretty popular. But recently they came up with something called Tetragon, which is like which enforces security policies at runtime. So it can like block privilege escalation attacks and stuff like that. And
Yeah,
everything uses BPF under the hood.
yeah, nice.
Yeah.
However, like, so security is getting a lot of attention. Performance is not. Like, if you see all the BPF kernels that are advertised, like it can do all cool things, those kernels are written by Meta, Google, like the big companies. We do not have like any startup which says, okay, we will monitor your performance, like just enable
Yes.
performance telemetry, like in a very easy way. There is like, I don't even know if there is any company doing that.
There is there was a company which I forgot the name. What was that? But they got acquired by Elastic, and they basically allow you to do continuous profiling. So you're talking about that, right?
Yeah,
A dashboard based, like you constantly profile your CPU, low overhead profiling, and then you see flame graphs and bottlenecks
yeah.
at like runtime. Yeah. So there is a startup. Let me see what Elastic. Yeah, they bought someone, but I I forgot. So this was like the startup from Halvar Flake, if you like know him, like he's a security person, but that was their startup. Yeah, just a second.
I think there are also articles from Brendan Gregg who worked on
Yes,
Linux
yes.
Perf and
Yeah.
Like he works
This is
it's
the
not
one I
like
was talking.
there are not like small startups like coming for to
So this is
like
the link
disrupt.
for the profiler. Like this works across all languages, and like under the hood is it is using Perf and BPF.
Yeah,
So to do continuous profiling. So this is similar to what Google, Meta, etc. have in-house. Like they have continuous profiling to continually see, like like show up like where the time is being spent the most.
yeah. This it's probably like these are like new areas where if you want to do some and explore things, this will be very interesting.
Right.
Another area I like. So what I am interested in is I'll come to your question, Girish. Like I'll just want to mention one thing before I forget. Um, with the new features like K pointer and basically tracking of the ownership semantics, what is
Yes.
happening here is we can now lower a high level language, let's say Rust, or there are other languages which
Exactly.
are more strict than Rust. Rust is strict, but it still has like holes. Okay.
Right.
So there are languages which enforce true move semantics. Like in Rust, you can do like trick around with that thing. So when you have true move semantics, that is when you can track ownership in a like the truest way.
Right.
And let's say you have a language like that, and then you can directly lower to BPF. So you do not have to rely on a virtual machine or something to.
Right.
So you'll have performance benefit as well as like a nice programming interface there, where you can do things which is which was just not possible with in C++. It's just almost impossible to do those things. So that will enable a whole lot of technologies like down the road. So, this is like really interesting for compiler folks to look at. Let's say you can take Rust itself, and how do you lower to BPF with this K pointer? So Rust would have some data structure which have enforcements on like move semantics. So instead of lowering to x86, doing a bunch of checks here and there, directly lower to BPF like with high level bytecode so that it can be verified at runtime as well. And it's I think that is it's going to change the way people program in certain domains.
Yeah. So this is like the whole idea to separate the front end and the back end. So this is why the verification. So there are downsides because so when people were adding support for loops, basically at the bytecode level you lose the loop structure, right? You lose the invariant of the loop and stuff like that. So it was pretty hard to actually add loops to the BPF ISA, like BPF verifier. But yeah, like eventually people got it to work using different tricks, like recognizing pattern recognition and stuff like that at the instruction level. But yeah, this is the whole point of like separating the language from the ISA.
Yeah. So Girish has a question: is there a possible use case for eBPF for software enclaves, trusted computing?
Yeah, I would think so because so far nobody has done that. Maybe possibly because SGX is kind of going out. So I don't know if it is going out, but there were some problems with that. But it is possible to use it for that. You can run your programs in a trusted environment. There are also other opportunities of ensuring isolation. So you can basically have address space isolation for particular BPF programs where basically your page table is switched on entry to the program and switched back. So it is like a context switch into a process where the BPF program at runtime does not have access to more memory than it needs. So it can be like a hardening feature on top. But basically the cost is the page table switch. So yeah, so it should be possible, but like anything is possible. So it depends on your imagination. Yeah.